Hello, this is Professor Hildebrandt. This is a content lecture for the second half of Chapter 13 on correlation analysis and linear regression. If you have not watched the first video that I posted, please go watch that first. I go through correlation analysis, and now in this video we will focus on linear regression. So for the second half of the chapter, we're going to be looking at another method for examining the relationship between two variables, and we call this regression analysis. This analysis also uses the basic concepts of correlation, but it provides us with more information because it expresses the linear relationship in the form of an equation. And so what we're going to be doing here, we're going to try to estimate one variable based on another. And so the variable being estimated is always called the dependent variable. And the variable that we're using to make our estimation or prediction of the value is the independent variable. Once again, the relationship between our variables is going to be linear. And also, just like in the first part of the chapter, both the independent and dependent variables must either be at the interval or the ratio scale. And as I mentioned earlier, we will have what's called a regression equation that expresses this linear relationship between the variables. So now let's talk about this idea called the least squared principles. The main objective here of our regression analysis is to use the data to position a line that best represents this relationship. And we could just go back to that scatter diagram that we've been talking about, and we could visually position the line. Here on the left, this chart here, we've taken 4 different individuals, and using their best judgment, we told them to draw a straight line that best represents the center of the data. And so you can see we have 4 different lines that people drew, and really except for line A, it's kind of the outlier up here, all the other 3 do seem to be centered around the data. But what we're really looking for is one line. What would be the best representation of the center of our data? And the method that's going to result in a single best regression line is called the least squares principle. So let's look at that some more. So the definition's up here in the green chart: a mathematical procedure that uses the data to position a line with the objective of minimizing the sum of the squares of the vertical distances between our actual y values and predicted values of y. So here's 3 examples to try to show you what this is talking about. And the first one here on the left that I've circled, that actually is our best representation. That is the least squares line. But just to kind of understand what you're seeing here, the dots in each of these 3 graphs represent actual values of y from our data set. And then the asterisks are predicted values of y given a value of x. And so if you look at chart 13.9, again, the one here on the far left, it is the best fitting line, and it's drawn using the least squares method. We know that it's the best fitting line because the sum of its squares, of its vertical deviations from the minimum, it's the lowest that it could be. It's 24. So for example, the distance between this dot and this asterisk is a value of 2. The distance between these 2 is 4, and the distance between these 2 is also 2. So if we square each of the differences, we would end up with 4 plus 16 plus 4. And so the least squares here are 24. If we look at charts 1310 and 1311, and we sum up the squares of their differences, we would get 44 and 132. So again, the chart here on the left has the least amount of differences at 24. So now let's get to our least squares regression line. It's actually going to take just a general form of a regular linear regression. It's going to really just look like the same as the equation of any line, going back to your math classes where you had y equals a plus bx, or perhaps in your micro class, you might have had an equation for supply and demand, and it was P equals A plus B cubed. And so this is the same kind of formula here, but we're going to be finding what we're going to call specifically the linear regression. So this one is called y hat. That's how you would say this first variable here. And it's the estimated value of y for a selected value of x. So y hat equals a, where a is the constant or the intercept of the line, plus bx, where b is the slope of our line, and then x is the value of that independent variable. We also have formulas to help us find a and b. So formula 13.4 here says that b equals that r that we found in the first part of the chapter, the correlation coefficient, times, and then we take the standard deviation of y and divide that by the standard deviation of x. When we calculate our slope, if we get a positive value for b, then that's going to show us that there is a positive or direct relationship between the variables. And if we were to get a negative value, then that's going to indicate an inverse relationship. It's important to remember that our y variable is the dependent variable and our x variable is the independent. And then the last equation here, equation 13.5, this is how we find our y-intercept, or the a variable in the linear regression equation. And here we simply take the sample mean of y, and we subtract the product of the sample mean of x times the slope that we found earlier, or our b value. So let's look at an example. We're going to go back to our copier sales. And the sales manager had gathered information, right, on the number of sales calls made and the number of copiers that they were then able to sell. So we're going to use the least squares method to determine a linear equation to express this relationship between the number of calls made and the sales of copiers. So first we have to find our slope, or the b. And so again, we're going to use the formula from the previous slide. So b equals, well, we found our r, the correlation coefficient, to be 0.865. And then we also, again, the textbook walked you through using Excel. We found those standard deviations for y and the standard deviation for x. And so we find that our slope is 0.2608. Step 2, we need to find our a. So again, we're going to use the third formula given on the previous slide. So we already know that the mean of our sample for y was 45 and the mean of the sample of x was 96. We plug in the slope that we just found and we find that our y-intercept has a value of 19.9632. Step 3, we're going to write out that equation. So we would say y hat equals 19.9632 plus 0.2608x. So what does this mean? Well, let's say our salesperson makes 100 calls. So we're going to plug the 100 in for our x value. Then he or she could expect to sell approximately 46.0432 copiers. We can also draw out the regression lines on a scatter diagram. And so this was talking about if we had a fifth guy named Jeff and he made 164 calls, then his estimated number of copiers is 62.7. And so we would draw that point here, 164 for x and 62.7344 for our y. And then the other points on the regression equation could also be determined by substituting in particular values of x and calculating the estimate of y, or y hat. And they've done this here. They've plugged those into the table, all those estimated cells, and then drawn out the regression line. Important to note, the regression line will always pass through the mean of variables x and y. And again, there's not going to be any other line through this data where the sum of the deviations is smaller. So this is our best line. And again, here's our formula down at the bottom. So the next step is to conduct a test of a hypothesis test to see if the slope of the regression line is different from 0. So we're going to test it for significance. And if we do not reject the null hypothesis, then we're going to conclude that there is no relationship between the two variables. But if we find that the slope is different from 0, then we can conclude that using the regression equation adds to our ability to predict the dependent variable based on the independent variable. Once again, when doing this, just like we did with our test of the correlation coefficient in the first part of the chapter, we're going to use a t-test, and we're going to use n being the sample size minus 2 for our degrees of freedom. We use the symbol beta to represent the population slope. So our hypothesis statement would be the null beta equals 0, so the slope of the population's regression line is 0, and then the alternate is that the slope is not 0. So again, once again, we're going back to the copier example. We've already found the slope, and we're going to use that as our estimate of the slope of the population, or beta. This is cause. So for this example, they've decided to use a one-tailed test. So our null is that the population slope is less than or equal to 0. And then the alternate is that it's actually greater than 0. So there'd be a positive relationship. We're going to use significance level of 0.05. Once again, we're going to use t as our test statistic. Our decision rule. So to figure this out, we're going to again go to that finding the critical value by using appendix B5. Our sample size here was 15. So for our degrees of freedom, 15 minus 2 is 13. And at a level of significance of 0.05, we would find the critical value to be 1.771. So we reject the null hypothesis if our t is greater than 1.771. This formula here, 13.6, is what we're going to use to test for the slope. And we get a t-value of 6.205. And so because of that, we do reject the null hypothesis, and we conclude that the slope of this line is greater than 0. What is our interpretation? The number of sales calls is useful in estimating copier sales. All right, the next part of this chapter looks at evaluating how well this regression equation actually is predicting. In reality, perfect prediction is basically impossible, and this is true for almost any discipline, including business, economics. So going back to our example here, this was our regression equation for the relationship between the sales calls and the number of copiers sold. And so let's examine if the number of sales calls made was 84. And based on our equation, we would estimate that the number of copiers sold would be 41.87. We actually did have 2 employees in our data set with 84 sales calls each, and they only sold 30 and 24 copiers respectively that month. So what does this mean? Is our regression equation a good predictor, or is it not? We need a measure here that will help tell us how inaccurate the estimate might be. So to do that, we're going to have this new statistic here called the standard error of the estimate. And this is really the same concept as the standard deviation in Chapter 3. So what this is going to do is going to measure the variation around our regression line, or that dispersion or scatter. It's got some characteristics here. It'll be the same units as the dependent variable. It's based on squared deviations from our regression line, and a smaller value for the standard error of estimate indicates that the points do cluster fairly closely around our regression line. And so here, formula 13.7 is the formula that we're going to use. Again, going back to the example that we've been using here, we are taking our information and going back to this chart that we've kind of been using, but now we're subtracting y from those estimated values of y, that y hat, and then we're squaring that because that's what we need for our equation here for the standard error of estimate. And so the sum of all of those differences squared is 587. We then divide by n minus 2. We take the square root. And so our standard error of the estimate for this example is 6.720. And you can actually, once again, you can calculate all of this using statistical software such as Excel or a similar program. Something else that we use to provide, I think it's thought of as like it's easier to interpret, basically a measure that's more easily interpretable of a regression's ability to predict is called the coefficient of determination, or more, this one is more commonly referred to as R squared. And you can really kind of ignore this formula down here, 13.8, because the reality is you just take that coefficient of determination the coefficient of correlation from earlier in the chapter R, and you square it, and that's how you get your R squared. And this is going to show us the proportion of the total variation in our dependent variable Y that is explained or accounted for by the variation in our independent variable X. It'll range from values of 0 up to a value of 1. Again, it's the square of the correlation coefficient, so that's why it's called R squared. If we go back to our copier example, we found our R to be 0.865, and so if we square that, we get an R squared of 0.748. So that is our coefficient of determination, or again, we would say our R squared. We then typically take our R squared and we convert it to a percentage, because that helps it make more sense for a lot of people. And so for our copier example, we could say that 74.8% of the variation in the number of copiers sold is explained by the variation in sales calls, which is actually a fairly good number. That's actually a pretty good R squared for a data set. So to kind of pull this all together, looking at the relationships between these, remember that our standard error of estimate measures how close the actual values are to the regression line. And so when it's small, then we know that our two variables are closely related. On the other hand, the correlation coefficient measures the strength of the linear association between those variables. And so when the points on the scatter diagram are close to the line, the correlation coefficient tends to be large. So what this really means then is the correlation coefficient and the standard error of the estimate are actually inversely related. So as the strength of a linear relationship between the two variables increases, the correlation coefficient will also increase, but the standard error of the estimate will actually decrease. I hope this helps you guys with chapter 13, and look for some more videos coming up with some examples.